All right, welcome to the University of Texas at Austin. This is the first part of Lecture 13 on digital pulse amplitude modulation, the first of two parts. So this part we're going to build upon what we know about in interpolation, sampling, pulse shaping. And we're going to put that to use to send digital data over a continuous time analog channel. And this is more generally useful for sending data across all kinds of channels. It could be wireless, wired, it doesn't matter. It's a very useful approach. We'll build upon pulse amplitude modulation in the next set of lecture slides, and then we'll go more depth. And then after that, we'll talk about quadrature amplitude modulation, but the digital version. We've talked about the analog continuous time version before in quadrature amplitude modulation. So this is Lab 5, right? We started already this week. And Lab 6 will be quadrature amplitude modulation. Quadrature amplitude modulation is just two channels of pulse amplitude modulation combined. All right, so today we'll talk about introduction to pulse amplitude modulation. We'll get to pulse shaping, and that's where we'll stop. And then next lecture, we'll pick up on the filter bank and design trade-offs. The symbol recovery is optional for the lecture, but you'll talk about this in the lab. All right, so let's talk about introduction. We're going to start with a digital bit stream, and we'd like to be able to communicate that over an analog continuous time channel. So we start out digital and discrete time, but we have to eventually transmit a waveform that's continuous time and analog in amplitude. So we're going to convert, so first thing we're going to do is we're going to convert a bit stream into a pulse stream. And that is to say, it's all at baseband at this point. And then we'll have some other steps. This is going to be the signal processing block in the communication system. After this processing, there'll be additional analog circuitry for power amplification. If it's, it might be an antenna. If it's RF communication, there might be another filter. There might be some adaptive systems. So there's more processing after this. This is just the baseband part of the story. All right, so we're going to take a stream of bits, conceptually infinite in duration, and we are going to group them in blocks. So we'll take a stream coming at us of bits, shown on the bottom here in the block diagram. So I have a bit stream, just a sequence of bits. I'm going to group them into a symbol of j bits. And j could even be 1. So we could do 1 bit per symbol. And by symbol here, we really mean a symbol like an alphabet, like a character in an alphabet, a symbol on a keyboard. All right, so there's going to be a finite number of possible symbols to transmit, and the receiver knows what these possibilities are. And the receiver is going to try to figure out what's the most likely symbol to have been transmitted. And the receiver has a lot of work to do to make that decision in a reliable way. There will always be some error in that receiver decision. Okay, so I'm going to group streams of bits into symbols of j bits. What I show on the right here, oh, one more step. And then we're going to take the symbol of bits, capital J bits, and we are going to map that into an amplitude. This amplitude will be real valued and unique. Okay, so the amplitude now, relative amplitudes matter. Okay, this allows us to do some nice things on the receiver side. We can do automatic gain control, for example, and all this stuff works really, really well. Okay, so what I show on the right is an alphabet of 4 symbols. This would be the case for j equals 2. So 2 bits or 4 levels. And I have to have, I'm on the transmit side, so I'm going to take my symbol of capital J bits, here j is 2, and I can send 2 to the j symbols. And j can be large. In practice, j goes all the way up to 15 in DSL. It's a lot of possible symbols, 32,768 symbols. More commonly, we're down in the 2 to 6 range for a lot of digital communication systems, Wi-Fi, for example. Okay, but anyway, j can be as high as 15. But for simplicity, I show you j is 2 here. So 2 bits, 4 levels. And we're going to take a symbol of bits, which is shown here on the left-hand side, and map it to a unique amplitude. Go ahead.
When you have that many bits, don't you need like a very large kind of voltage range?
Yes.
Like make sure the noise
Yeah, so the question is, as you get more and more bits or more and more symbol levels, you need a wider dynamic range of voltage. Yes, this also depends on the value of little d, which we'll get to. So yes, and this puts a lot of stress on the analog circuitry after we're finished with our digital discrete time work. This puts a lot of stress on the D to A converter and subsequent processing, because we have to sustain a more or less a linear response to the range of voltage values that we're using for our amplitude representation. Absolutely. It also means it also impacts power. Right, so let's get on to the mapping, and we'll talk more about that. So the map, so for every 2 bits that I group, I have 4 possibilities, and I can encode this many different ways. This is just one way to encode the data. So for 0, 0, I'm going to map this to a real amplitude, little d. And for 0, 1, I'm going to map this to an amplitude. Okay, someone. All right. And then for 1, 0, we map to minus d, and then for and then for 1, 1, we map to minus 3d. Okay. I'll turn it off, I think, is a good. I cannot. Oh. You know which one it is? This one? And how do I. Yeah. Oh. Or even better, exit. All right, thank you. All right, let's get back to our discussion. All right, so we have mapping from these 4 possible levels, bits, I'm sorry, 4 possible bit patterns to 4 possible levels, and we have a free parameter, which is little d. And little d is going to determine a lot of things. Our voltage range, it's also going to determine the amount of power that we consume, ultimately. And so little d here is a parameter. So if we look at this, the voltage swing, we know we need to at least represent voltages from minus 3D to 3D. And we're going to see we need a little more than that. But we know we need at least that much. So if D is large, say D is 3 volts, then we got to go from minus 9 to 9. It's a pretty big swing. Pretty big range of voltage to cover. We also know that power is proportional to amplitude squared. So we know that the power, the maximum power possible, the peak power, is going to be proportional to the amplitude squared, and the highest amplitude we have is 3D, so the peak power here is proportional to 9D squared. So there's a trade-off. So we increase D. The good news is that it improves our signal power. That's good news. That means we have more signal power that will get to the receiver, and hence we have a higher ratio of signal to noise power. The bad news is higher the D puts a lot of stress on the analog circuit design to follow this in the transmitter, and stress on the receiver side. More complexity, more cost. There's a trade-off. There's also, generally in the communication systems, anything that uses a regulated band, whether it's licensed or unlicensed, there's a limit to how much peak power you can put into that transmission band. So in many standards, there's an upper limit on what D can take, or what the peak power can take. There's also a notion of average power, which is on average, how much power do we consume? And so if we look at this, and if we assume that all the symbols are equally likely, the possible powers here are 9D squared for the peak power. So our peak power would be 9D squared. The other option would be D squared. So on average, how much power would we consume, assuming equally likely transmission of these symbol values? 5D squared. That's our average power. So the peak power is 9D squared. The average power is 5D squared. Just the average of these two. Right, it's the average of the power used by 3D and the power used by D. We only have to look at half the story because the other half is just symmetric with the top half. So the bottom half is symmetric with the top half. Okay, so we have our amplitude values, which is great. The next thing is to figure out how to get these amplitude values encoded into a continuous time analog waveform, and now this is where the pulse shape choice comes into play. So what we're going to end up doing is we're going to scale the pulse shape, whatever we're using, raised cosine, rectangular pulse, be a truncated raised cosine, truncated sync, whatever it happens to be. We're going to scale that pulse shape by the amplitude value. And by amplitude, we really mean the real value here, the real value amplitude that we've mapped to. So this is M-level PAM, or simply M-PAM. And again, M is the number of levels, and the number of levels is 2 to the power j. We're transmitting data at a certain rate, and this is the symbol rate. Okay, so now what's very quickly going to happen, it's not happening so much yet, but it's going to happen soon. We're going to have 2 clocks pretty soon. Right now we just have one to worry about, which is the symbol clock. So for every symbol period, we're going to send j bits, capital J bits. So another way you can think about this is the bit rate is the number of bits per symbol times the rate at which we're sending symbols. So it's capital J times the symbol rate fsim. Now, to do the conversion from discrete time to continuous time, we've talked about this. We spent lecture 7 on this, and we're going to reuse those ideas here. So first we'll do, so we need to just convert from discrete time to continuous time, and we'll do that the way we're doing it here is in 2 steps. Okay, so the first thing we're going to do is use an impulse modulator, which is to say this is an impulse train, and we're going to scale, this is theory, we're going to scale the area of each impulse train based on the symbol amplitude value in that symbol time. So each symbol time will have 1 impulse, so the impulse train is separated by the symbol time in the time domain, and I'm going to scale the area by the value of the symbol amplitude. Now, again, this is theory, but even in theory we have some issues here because I have an impulse train, and what kind of bandwidth does the impulse train use? All of it, right? The Fourier transform of an impulse train is an impulse train. We're back to problem 0.1 in the homework set, my favorite problem. It will continue to be my favorite problem. It may become your favorite problem after enough time. So this is taking up infinite bandwidth using the impulse modulator. Well, in communication systems, we don't get to use all possible bandwidth. We're limited to some band. So we're going to follow this with an analog continuous time filter, but this filter will be finite impulse response, which is a little unusual for an analog continuous time filter, but they do exist. This is a tapped delay line, or something like it. And so we're going to do a pulse shaping here. This is the theory side. We'll get to an implementation that we'll do in lab in just a second. So we're going to filter this impulse modulator, which has all frequencies in it and harmonics of the symbol rate. We're going to low-pass filter that. So band limit as best we can. Can't exactly band limit, but to at least low-pass filter this output of the impulse modulator. Okay, so what does this impulse modulator output look like? It's going to be a pulse train. Again, this is theory, so we're going to kind of hard to build an impulse train in practice. We can do it with really narrow rectangular pulses, about the best we can do. All right, so what's going to happen is I'm going to have the output of the impulse modulator. It's going to be a series of impulses. And these impulses will be separated by the symbol time. And the area will be scaled by the symbol amplitude. So here the area under this direct delta is the symbol amplitude at symbol index 0. So I tried for the rest of this, for the next set of slides, I'm pretty consistent, try to be, that little n is going to refer to the symbol index. So I'll do my best on that one. So here's A1, here's A0, sorry, there's A1, A2, and so forth. So the area, and again, the area could be negative, it doesn't have to be positive, right? The area could be, you know, any of these choices. It could be 3D, D minus D, or minus 3D, any of the amplitude values in the constellation map, in this lookup table That's all it is. It's a lookup table with m entries. In this case, j is 2. I have 4 entries. I have an array of 4 values, and I can look up the value simply by using this bit pattern of the symbol of bits as my unsigned index into the lookup table, right? So if I look at this as, these are just basically entries into a lookup table, and 1, 1 would be the unsigned index into that lookup table. So it'd be 3, unsigned. So an array of 4 values, 0 maps to D, entry 1 maps to 3D, entry 2 maps to minus D, and entry 3 maps to minus 3D. So very fast to implement. All right, now the impulse train again, it's nice theory. So what I'm going to do is I'm going to filter the output of the impulse modulator with a pulse shaping filter, and I'm going to convolve in the time domain, and then in the Fourier domain, I'm going to multiply the 2 Fourier transforms. So in the time domain, this impulse train now looks like a sequence of what? I heard sinks. Well, it's whatever the pulse shape is, right? It's a sequence of pulse shapes now. And those pulse shapes are now going to be scaled by A1, A2, A0, A1, A2, etc. So if I were to use a rectangular pulse, which is the easiest one to draw, so if you really have to draw one on a test, go with rectangular pulse if you have the choice. It's the easiest one. So I'll have A0 for a while. Let me get... So this would now be S star of t, the output of the baseband modulation here. So I'm going to start, so I'll have A0, whatever A0 happens to be. That will be held until I get to T-sim. And then the next symbol amplitude gets held. Let's go ahead and go with 3D on that one. And then the next symbol amplitude, which would be A2, that gets held. So we can call that minus D if we wish. Right, so that's my transmitted waveform. Sorry, that's my baseband waveform for transmission. I have other steps to do. There'll be subsequent filtering steps and up conversion. Go ahead.
So you're saying that the symbol amplitude being multiplied by that impulse train, and then then the pulse shaping block is because tapping into the pulse that you want.
Do you remember? Yes. Do you remember when you convolve with the Dirac delta? All you do is you shift the signal you're convolving with, and you're going to scale it by the area, right? So this Dirac delta mathematically is A1 delta T minus capital T sim, right? Got it. And so when I convolve it with the pulse shape, I get the pulse shape shifted by capital T sim and scaled by A1. Okay, good. So then if I had to fill in these entries, this is A0, this is A1, and this is A2 in amplitude. Right, so I've gone with D for A0, 3D for A1, and minus D for A2, just for illustration purposes. Now that's staircase approximation. We know this is, remember, this is just this cascade of the impulse modulator and pulse shaping filter is really just my discrete time to continuous time conversion step. I've got to follow this with subsequent filtering to get rid of the artifacts that I've introduced. Okay, and so there'll be, again, this is just what happens at baseband. There'll be another processing stage after this before transmission finally happens. This is just the baseband part. So at least has to be subsequent filtering. Okay. All right, so let's, this is probably the most important slide in this part. That's what you're going to implement a version of this, which we'll get to in a second. But we're going to replace the impulse modulator and the pulse shaping filter with stuff in discrete time, blocks in discrete time, and then we'll go ahead and throw a digital to analog converter into the story. It's sort of making sense. Okay. Okay, now this is just in slides what we've just talked about in words. So in pulse shaping, if we don't have pulse shaping, if we're without pulse shaping, then we get one impulse per symbol period, and and infinite bandwidth is used, and that's not practical. And that's what we've already talked about. So that would be the equation. If we didn't have pulse shaping, we'd have this impulse train whose areas are scaled by the symbol index. Here I've used k instead of n, but hopefully that's okay for the symbol index. Now, even theoretically, we like to limit the transmission in frequency. So we were to limit the bandwidth by pulse shaping using FIR filtering. And what it's going to mean is we're going to, as we pointed out last slide, it's going to be really, this should look pretty familiar now. Right? This is the final outcome of convolving the impulse train with the pulse shaping filter. And it should look exactly like what? I have a convolution. Well, this is with pulse shaping. So it's an impulse train. It's the output here of the pulse shaping filter. Whatever pulses it is, that's right. But the formula should look really familiar. The placeholder, it's convolution. It's a filter. Yes. Yes. Good. In this class, it's a good answer. All right. It is. I have the inner variable here of summation. The placeholder variable is in discrete time. The outer variable is in continuous time. I'm holding the discrete time signal in place, flipping and sliding the pulse shape, which is continuous time about it. This is interpolation. This is exactly lecture 7, slide 3. This is the interpolation. We did this. But now it's a different context. Now the A sub k's, this discrete time signal, are going to be our symbol amplitudes, and the pulse shape is going to be right now it's still in continuous time, but we'll convert it to discrete time in just a second. So I have to choose I have to choose a symbol period, a pulse shape, and a constellation map, and I'm good to go. And it's a bunch of filtering. So it's so what I have. I have, if I look at the block diagram down here, I've got group the bits in the J bits, do a lookup table to map from the symbol of bits to symbol amplitudes, the symbol amplitudes A sub n. I multiply by an impulse train in the time domain, and I filter. Multiplying by an impulse train is another model for sampling. So we're sampling at the symbol time at the impulse modulator block. Right? So this is another way of doing sampling. Okay. As you might guess, we could move the sampling later, which we'll do, and do the filtering in discrete time, which we'll do in just a second. All right, if we look at the formula here for S conjugate of T, then this is my interpolation formula for an input signal that's discrete time and an output signal that's continuous time. This is our discrete time to continuous time conversion. In the previous slide, the pulse shape G of T sim only lasted one symbol period. We used a rectangular pulse. More generally speaking, for a pulse shape that lasts a longer amount of time, and n sub G is simply the number of symbol periods that it lasts. And then T sim is the symbol time in seconds. So the duration of the pulse shape will be some integer multiple of the symbol time. Then we'll get n sub G pulses will overlap in each symbol period. Right? So if we have a rectangular pulse, n sub G is 1. No overlap with other symbol periods. If our pulse shape's a triangular pulse, what's n sub G? How many symbol periods wide? Linear interpolation. 2. Okay. And then we can use a truncated sinc or raised cosine, and we can make n sub G 4, 6, 8. In lab, you'll do 4, 6, and 8 between labs 5 and 6. This also relates to homework 4. All right, so let's look at 2-PAM transmission. This is a very basic and used widely. We use this a lot also in training signals when we have two modems that connect to each other. It's also known as binary phase shift keying, or BPSK. Has lots of different names. So for 2-PAM, I'm showing you an example now of S star of t, the actual baseband output, for the following scenario. I have a raised cosine pulse with peak value of 1. And then I have a string of zeros and ones I want to transmit. So my symbol is 1 bit. And I'm going to map 0 to -1 and 1 to 1. Okay, so the constellation map and I could just as easily, I suppose, map, bit of 0 to 1 and bit of 1 to -1. It just as long as the receiver knows what the map is, it doesn't matter. So a bit of 0 goes to amplitude -1, a bit of 1 goes to amplitude 1, +1. And you can pick off some features here of the baseband signal in continuous time, analog amplitude. Right. So now if I look at this, there's some nice, so I know that my symbol amplitudes are +1 and -1. And whenever I interpolate, I don't change the values, at least not from a linear system point of view. I don't change the values that I know. I just connect the dots. But I keep the dots that I started with the same value. So wherever I have -1 and 1, that's a good guess. That's actually one of the original symbol amplitude values. And the rest of the waveform is just connecting the dots with some pulse shape. Okay? Now the pulse shape here is, what's your guess of the pulse shape? Raised cosine. I have to guess at it. So raised cosine pulse. And I think it's 4 symbol periods. Forgot how I generated this one. But what I can view out of this is, I'm going to ask you 2 things. What is the value of, oh, that's right, what's the value of D? That's an easy one. D is 1, right? So D is 1. Right, because 0 would map to -D and 1 would map to +D. So D has to be 1. What's the symbol time? Yeah. And how'd you get that? The distance. So you can either eyeball the distance between adjacent symbol values. That's one way to estimate it, and you got 4 milliseconds. Another way to estimate it is using more points. I have 100 milliseconds over which I have to count it. I think it's 25. So I count the number of symbol periods or symbol values here, I should get 25. So 100 milliseconds divided by 25 symbols, 4 milliseconds per symbol period. So your eyeball is very accurate. Okay, so 4 milliseconds. So T-sim is 4 milliseconds. Now, how does the maximum amplitude relate to D? This is not an easy question at first. We know that we need at least, the amplitude range has to be at least -D to D, which is in our case from -1 to 1. We know we need that much. But you'll notice that as we connect, depending on the pulse shape, we actually have a larger dynamic range in volts than that. So it depends on, what does it depend on? D, what the peak and valleys are, max peak, max valley are. Depends on the previous values. So if it's all 1s, then I'm going to get the maximum peak. And if it's all -1s, I'll get the smallest valley, if we're done quite right. Okay? So it also depends on the width of the pulse shape. That tells you how many symbols are contributing to the current symbol time. So I get contributions from future and past symbols. I'll repeat that again. I get contributions from future and past symbols. That should bother you a little bit, because suddenly I'm non-causal here, unless I buffer, which is what we'll do in lab. So we'll buffer, so I don't have to worry about the going forward and backwards in time. I got all the time I need. Because the buffer, I delay the transmission. Okay. Now, a few insights here. So you'll notice here that the range right now for this is 2 PAM, and I think the pulse shape is 4 symbol periods is my guess. You have to know that to find the peak. But here I'm basically -2D to 2D is what I'm seeing here. So what you can do is simulate, if you really want to know just run a whole string of ones without scrambling, just a whole string of ones, see what the peak is, and put a whole string of minus one, or bit of value 0 to get -1 amplitudes to see what the valley goes down to. Because you got to know what the voltage range is, because that's going to determine the rest of your design later. All the analog circuitry that follows this has to handle more or less linear response over that range of voltage values. It also increases average power. You increase D, you increase average power and peak power. Now, the highest frequency possible, and we've seen this on midterm 1, and we've talked about it, the highest frequency possible in this context, because the only clock we have is the symbol rate right now, is half the symbol rate. So if we alternate symbol amplitudes of plus D, minus D, plus D, minus D, and so forth, the maximum frequency possible is half the symbol rate. Can't get any higher than that. So that tells us something about the pulse shaping filtering that we need to do. We want to make sure that we are we're rejecting frequencies above half the symbol rate. We're attenuating frequencies above half the symbol rate. All right, now let's make this work in discrete time, and we can implement this on the digital signal processor in lab, and we can do it in simulation in MATLAB, which is homework 4, and it'll be homework 5 and 6. We'll use PAM for quite a while in homework assignments. Even homework 8 has PAM on it. Okay, and even QAM is two-dimensional PAM, so we're going to be doing some version of PAM for the next 5 homework sets. All right, again, the transmitted signal is this discrete time to continuous time conversion. This is interpolation. Now, I can sample this interpolation. My input is A of K, so the input is AK, or A of N, really. K is just a placeholder variable for summation. So I have a discrete time to continuous. This is discrete to continuous conversion. This is exactly interpolation. And I get out this continuous time analog waveform. I can sample this equation that relates the input A of N, my symbol amplitudes, a stream of symbol amplitudes, with the output as conjugate of T. And if I sample this, I'll get an equivalent implementation using upsampling, FIR filtering in discrete time, and then we'll use the digital analog converter to convert from digital discrete time to analog continuous time. All right, so let's go through the sampling process. So we're going to sample at a sampling time. Now we have a second clock in play. We now have a sampling clock in addition to the symbol clock. And I'm going to keep them as separate as possible. So the symbol clock I'll identify as capital T subscript sim, and the sampling will capital T subscript S. So we'll let continuous time. I have two different clocks, and they're going to be related to each other, which is kind of nice. Because I'm going to have L samples per symbol period. Okay. And I know, so I can relate the symbol time and the sampling time. The sampling time is going to be as fast or faster as the symbol time. So capital L is some integer. It could be 1 for one sample per symbol. It could be 4. In lab, we use 4 and 16. So I can relate the symbol time to the sampling time. I can also relate the sampling rate to the symbol rate. All right. So for every symbol interval, so over a symbol time in seconds, I'm going to have L samples. So the sample index, I'm going to try to use as little m. Go ahead.
So the sampling, like the sampling time, that's only for the analog side of things, right?
The symbol time is for both. The symbol time is for both the analog continuous time side and the digital discrete time. The sampling time is going to be really is going to drive the D to A converter.
Okay.
Right. So that's why we like to be able to, we want to convert the previous equations into discrete time equations, and the sampling rate that we choose will feed in, that's what the digital analog converter will reference, or equivalently the sample time. So again, little n is the index of the current symbol period, little m is the sample index within the nth symbol. So I have, here is symbol 0, here's n is 0, this is symbol 0, and m is 0, 1, 2, 3, right? So m is the sample index within the symbol period. So you're going to have two dimensions to worry about, even though it's time is one-dimensional in seconds, but I have two ways to index into that. The symbol index and then the sample within the symbol index. So the way I can find where I'm at in terms of samples is I give you the symbol index, little n, and then the sample value within that symbol period. So if I give you n is 0, m is 2, I would pick up so this would be n is 0, m is 2. If n is 1 and m is 0, that would be this one. So here I start, this is now n equals 1. Okay, and so forth. So m is limited in value. M is only valid from 0 to capital L minus 1 inclusive. There's a finite number of possibilities. N is an infinite number of possibilities. Now if we go ahead and go through the sampling on this, we're going to replace little t with little n, L, plus little m, that quantity times the sampling time. So I'm replacing little t with little n plus capital L, sorry, little n times capital L, right? It tells me, so what my symbol index, I can find out what sample I'm going to, where I am on the time axis by multiplying the symbol index by L. And then I find out where I am within that symbol period by knowing what little m is. So if I sample this, I end up with, in discrete time, is once I've sampled at the sampling time, I now know that I can just worry about discrete time now. I can abstract away the sampling time. And so my index of the discrete time calculation for S star, which is here, of is the following. So A sub k doesn't change. That's not dependent on continuous time little t. This little t is, and so I can replace little t with, again, n times L plus m, quantity times t sub s. T sim here, this is the same as LTS. So now after sampling, what's in the argument for the symbol, for the pulse shape, if I do the sampling here, I get, find a place here, I get GT sim, little t is NL plus M TS minus K L TS after sampling. As a discrete time signal, my discrete time samples are taken with respect to the symbol time, the sampling time, capital T sub s. So in terms of discrete time, I'm left with L times n minus k plus little m. So that's my index into the symbol time. Or sorry, the pulse shape using the symbol index little n and the sample index little m. All right, that's a long way to go. What we're going to do in terms of the block diagram is replace the discrete time to continuous time conversion step, which was impulse modulation and FIR filtering and continuous time, with upsampling by L, FIR filtering, standard FIR filtering, and a D-to-A converter. So the upsampling by L, if you think about it, is impulse train modulation. I get an impulse train out. What the upsampling does is it copies whatever value at the input to the output and then appends L minus 1 0. Input to output, append L minus 1 0s, I get an impulse train. And the amplitudes represent A sub n instead of, it's a discrete time impulse train. So the amplitudes are keeping track of A sub n and not the areas. Then I will filter that with a low-pass filter, my pulse shaping filter, to get out my discrete time baseband signal. And I'll send that through a D-to-A converter to get the continuous time analog version of that baseband waveform. All right. Let's kind of walk through this and do a real simple example, make it a little more clear. All right, so now my processing stages are the following. I want to take a symbol of, stream of symbol amplitudes A sub n, which is at the symbol rate. I want to pass it through an upsampling filter. The upsampling filter increases the rate, the new rate on the output of the upsampler, because I have L times as many samples as the input. I increase the sampling rate by a factor of L. And this is equal to the sampling rate. I then apply an FIR filter at the sampling rate, a pulse shaping filter, and then I pass it through a D-to-A converter, and the D-to-A converter is operating at the sampling rate. Then I have a baseband waveform for transmission, and at the very least in the next step in the transmitter, after the baseband processing happens, I got to at least apply a transmit filter to limit the bandwidth, limit most of the energy to be the bandwidth I can use for actual transmission for the communication system. So again, upsampling by L, which is denoted by this up arrow, and that up arrow implies that the sampling rate's increasing by a factor of L from input to output. And conceptually, all this does is for every input signal, for every input value, I'm going to output the input value followed by L minus 1 zeros. I'll show you that in a second. And we convert symbol rate to sampling rate. We then do the pulse shaping filter at the sampling rate. And what this will do is interpolation for us. This will fill in the zero values that the upsampling inserted to get us to have a smooth signal. Now, a result of that is that I end up multiplying by 0 most of the time, which is not efficient, and we'll fix that inefficiency later. So let me walk through the simple example to kind of make it more concrete. So a simple example here is it's actually used in an audio converter, the D-to-A converter for audio, but it's the same idea that we just had. It's interpolation. So I'm using, in this example, CD audio, original format, 44.1 kilohertz sampling rate, 16 bits per sample. I'm just looking at one channel, not both of them, just for simplicity. And what I can do in a digital analog conversion is to do some upsampling to give me some room to make filtering easier and subsequent processing easier. And we'll talk more about that in data conversion, or we will in lecture 10, I guess. So if I upsample by 4, it means that for every input value, I copy the input value to the output and I append 3 zeros. So what does that look like? So here's my input to the upsampler. For every input, I copy it to the output for upsampling, and then I append or insert L minus 1 zeros, 3 zeros. Go ahead.
If you're like the signal, you end up having where, you know, for every one sample, you actually have 4 samples. Oh, never mind. I just answered my question. All the way different question. Why is the, like, when you have the FIR filter, how does it know to, like, to interpolate between 0, 4, and 8 and not interpolate those 1s and 3s like dips?
So you choose. So you have to choose the FIR filter so it does not alter the points you know. And what we'll see how to do that a little bit later. So the next sample comes into the upsampler. I copy that to the output and append 3 zeros. And I keep doing this. And you look at this, this is an impulse train now, separated by the number of samples per symbol, L, which is 4. I then apply the FIR filter. The FIR filter is going to then basically fill in the values that are 0, keep the samples that we know the same, and then fill in the 0 values as we go. And to get a smooth output. It's a low-pass filter. It's supposed to do smoothing.
But normally, like just a standard FIR filter that we've learned in class might not actually have this effect. You have to put special things in there to make sure that it only will affect certain samples.
That is, I think that is correct. We'll talk more about this filter design as we go. Okay, so we'll revisit this on Monday. So we'll see you on Friday.